I'm Professor Stanley Chang. This talk will be recorded. I have the great pleasure of introducing our colloquium speaker, Dr. Diane Hoffus. Dr. Hoffus went to Virginia Polytechnic for her BS in 1989. She then got a PhD at the University of Santa Barbara in a subject called hyperbolic three manifolds, which I consider to be like the hardest thing on the planet, right? She's very accomplished. She's now a professor at the University of San Diego University. Is that right? San Diego University.
University of San Diego.
San Diego University of San Diego. Okay, and recently she has a project that landed her on the cover of the mathematical bulletin and the mathematical notices, which never happens to anybody. Diane is probably the most gifted speaker that I know that I've ever met. And I'm sure that she's gonna give an amazing talk and inspire you to do something like what she does. All right, mathematical sculptures at Burning Man. Take it away, Diane.
Oh, thank you. Thank you so much. I'm so happy to see so many people here. And I'd like to thank Stanley, Dr. Chang, for inviting me. It's always exciting to get to talk to him. And I'm really excited today to talk to you about something that was been really meaningful to me over the past couple of years. I'm gonna be careful to end after 50 minutes because I want to leave some time for questions. And I'd really love to hear your reflections. But also, I've got the chat window open, and I'm totally open for anyone to interject if they have questions. I'd love to have some interactivity if that's possible in this sort of awkward Zoom land. Okay, so today I want to tell you about this experience I had creating a mathematically based sculpture and bringing it to Burning Man. And having talked about this sort of thing before, I know that, you know, there's some common questions that come up. And one of the questions is, what is Burning Man? So Burning Man, there's a lot of answers to this question. At its base level, it's an annual event. It was started in 1986 by Larry Harvey and Jerry James in this small beach called Baker Beach, a little bit north of San Francisco. And then in 1990, it grew and then moved to the Nevada desert. It's about 100 miles northeast of Reno, on this dry lake bed. It's a temporary community, an experimental community, organized around 10 principles. And I'll just tell you about a couple of them. One of them is radical inclusion. And that means everybody is welcome. Everybody is welcome to be a part of Burning Man, to engage in any of the things going on at Burning Man. It's very inclusive. Another principle is leave no trace, which is taken very seriously. That means everything you bring in, every single thing you bring, you must also take home with you, to the tiniest splinter and any piece that you would drop. People are very careful to bring it all away. Another one is gifting, and you may have heard of this and thought it talked more about bartering, but that's not true. You just come with a gift with nothing expected in return. And some gifts are physical objects and trinkets. Some gifts are, people will bring food to share. But some gifts will just be, for example, you can bring an art project for people to enjoy, or your theme camp can organize an activity, or maybe you just bring of yourself. You come to help build something, add your expertise, help somebody if their bicycle breaks down. So it's a very warm place. One principle that's important to me is participation, and you're meant to get involved with things. There was a exhibit at the Smithsonian at the Renwick, I think it was last year, called No Spectators, and it was about the art of Burning Man. And you're not meant to be a spectator. You're meant to step in and experience things, participate. Okay, so here's an sort of bird's eye or like plane's eye view of Burning Man, the Black Rock City, which is the city that Burning Man takes place in. I think this was from 2018. Which was the year I was there. And you can see this Pentagon this Pentagon is a fence around the area that Black Rock City, that Burning Man takes place in. And this arch, this sort of partial circular arch, that's the city itself. That's where everybody lives, the camps and the sort of homes are all there. This is a big city, so it's about 75,000 people now. And so I looked up some statistics on Wellesley, and I think that's 30 times the population of Wellesley. So to give you a sense of that. This event takes place the last week of August and the week right before Labor Day. And it ends on Labor Day. Everybody goes home on Labor Day. I'd like to orient you a little bit to this, to what's going on in this. So if you look at the center, I hope you can see my little mouse. If you look at the very center of the circle, this is the man. This is the man that burns, that Burning Man is named after, and the burning is meant to be sort of a sense of like tearing down and renewal for the next cycle. And everything else is oriented along this polar grid and is addressed like a clock. So up here at the top at 12 o'clock, this is the temple. This is the 3 o'clock and the 6 o'clock and the 9 o'clock portals. And everybody's address along here has to do with, where they are on the clock. Right here, this is center camp. This is where you can buy ice, you can buy coffee, and that's all you can buy at Burning Man. Everything else you need to bring. Another thing that's important to me is maybe something that you've noticed. There's all these little black dots everywhere, all these dots all out here in what's called inner or outer playa. Oh, yeah, James says bring water. Yes, absolutely important. They don't supply water. You need to bring your own water for the week. Does anyone want to guess what all these dots are in the inner and outer playa? Art, yeah, art. These are all sculptures. These are all very large scale sculptures. There's about 200 or 300 of them out in this sort of open area. There's certainly more art in everybody else's camp, but these are the ones placed by Burning Man. So this is a 7 square mile exhibition space for large sculptures. And just to give you a sense of that, so the height from the base of this Pentagon to the tip, that's a little bit more than 3 miles. You need a bicycle to get around. Here's a really awesome picture that I saw where somebody superimposed just the city on top of Lower Manhattan. So I just want you to have the scale that this is a large open area. Okay, you might also be wondering, why would I do this? Why would I, a professor of mathematics, want to build an art sculpture? Well, I've been a professor for 23 years, and I've noticed, maybe many of you have noticed this as well, there's some misconceptions about mathematics. So whenever people find out I'm a math professor, they'll say, oh, cool, what's the biggest number that you know? And, or they'll say, well, I'm sure you can, you're so good, you can probably calculate the tip at a restaurant. And of course I can, and I'm sure that you can as well, but this makes math seem dull. And I've really been interested in helping people understand the true nature, what's exciting about math, the kinds of problems that we work on. And at the same time, or not the same time, but recently in 2016, independently of any of this, a friend sort of mentioned Burning Man and said he thought I might like it because I just love lights. And there's so many really beautiful lights at Burning Man. He said, maybe you should go and see. And I did love the lights, but what I loved even more was sort of the openness of the people, especially their curiosity, sense of play and experimentation, open-mindedness. And I also noticed that a lot of the sculpture at Burning Man is very mathematical based. So this picture in the upper left, this is a bird's eye view of the temple for the year that our project was there, called Galaxia, this beautiful spiral. The upper right, the stack of truncated cubes by Kirsten Berg. The lower left is this amazing icosahedron by Haibikozo, and it has these carvings in the side of it and a light inside so that it stereographically projects the carvings on the side onto the ground. And then when you spin the icosahedron, then the projected images move as well. The lower right is also really cool. Actually, this is by Fold House. These are origami folding mushrooms, and you can see that the one on the left is squished down. There's these plates, this is part of participation. You step on the plate and it compresses the mushroom, and then you step back and it pops back up. So, so I thought it would be great to try to express what mathematicians think is so wonderful about math to this group of people who seem so open to these ideas. And I thought about what I could do for it, and I had what I thought were some good ideas, and but turns out I'm not a natural artist, and it was very hard for me to think of a way to express any of these in sculpture form. So I thought, okay, I'm just gonna take a year to think about what I really want to do, and I probably need some experience too. So I want an origami mushroom. So I found another project in San Diego, and I asked if I could join. That was called the Journey Project. And here's an image of it. So it was this giant double coiled torus with LED lights and sound and all sorts of things. And this is how all Burning Man projects go. This is all part of participation. You know, I came in to say, hey, can I help? And they said, sure. Oh, by the way, do you want to be the software lead and the lighting artist, and you can do all this stuff? And the next thing you know, I'm sucked in. But so this project was very complex, and I learned a lot. I learned a lot about what goes into creating such a large sculpture, the volunteer culture of Burning Man, considerations for doing construction in this environment. So this is a very harsh environment. The temperature is very high during the day, can be very low at night. There's very harsh winds. You're meant to be prepared for 100-mile-an-hour sustained winds. And so you really need to, there's extra considerations for doing this construction. I learned a lot about programming LEDs, but I think most importantly, I gained a really healthy attitude towards failure. And that seemed to be just what I needed to go forth and try my hand at this. So, but I needed a good idea, and, oh, sorry. And where did this idea come from? Well, there's a new geometer had just arrived in our department named Satyan Devadas. And if you've never had a chance to meet him, it's a shame, because he's a wonderful, interesting person who's excited about everything. And so I asked him if he'd like to join me in this. And of course he did, because he loves everything. And he suggested that we try to address an unsolved math problem. And so the way we went about this is he had a geometry class at the time and made an assignment that students themselves propose a sculpture that addresses an unsolved or recently solved math problem, interactive, to be in the spirit of Burning Man, and was designed around the Burning Man theme that year, which was iRobot. So 5 teams submitted, and we saw their presentations. We tried to go through, we presented 2 of them to Burning Man, and 2 of them sort of made first cut, and we chose one to go through with, and that was this one on an unfolding dodecahedron. This was proposed by the student team, Jordan, Nick, and Eugene. And so here's how they address those 3 issues. The unsolved problem is sort of Durer's conjecture, which I'll tell you about in more detail. The interactive part is that participants themselves could unfold this dodecahedron. And the iRobot part had to do with the relationship between humanity and technology. And I'm going to say more about all of these in a minute. So we love this idea, and we added a few things to it. For example, the character rain that from the Matrix movie, and on the outside, and some mirrors with the space theme on the inside. And here was our model. So this is what we were going for. And this beautiful rendering was created by the student Quinn Pratt, who's just talented in all things. And so armed with this is what we were going to try to build. And but before I tell you about building it, I want to tell you a little bit about the ideas behind it. So what about the unsolved math problem? So Albrecht Dürer was an artist in the 1500s. He was a painter, he was a printmaker, and he worked with Italian artists on issues of perspective, and he really wanted to understand three-dimensional things and represent them in two dimensions. And so this image on the slide is a page out of his notes, and these are three representations of an icosahedron. And each of them has their advantages and disadvantages, but some of them require, the two on the right require some distortion, or well, the upper right requires some distortion for you to see it all, and then the lower right requires self-intersections. The one on the left is the one that's relevant to the talk today. The one on the left is an unfolding. It's called a net. And the thing about that is there's no distortions. It's geometrically accurate. And if you cut it, you can fold it back up and create the icosahedron. So this leads to a question, can you always do this? If you take a random polyhedron, will you always be able to cut it along its edges so that it unfolds and lies flat? And specifically lies flat without overlapping, because if it overlaps, then you don't really have a true way to reconstruct the object. And that's actually been unknown for 500 years. And so let's talk about how you might approach a question like this. So first of all, the conjecture specifies convex polyhedron. And there's a good reason for that, because it's not true if the polyhedron is not convex, and we know that. So here's a non-example. I'm not saying this is a counterexample because it's not part of the hypotheses, but I want to use it to help explain to you how you might know that there's no way to unfold this, to cut and unfold without having overlap. So if you're unfamiliar or you forget the definition of convex, this region is non-convex because if you take some point in this upper cube and some other point in this lower slab and connect them with a straight line, that straight line exits the polyhedron. It doesn't live totally inside the polyhedron. Therefore this shape is non-convex. You can see that you can't unfold it to lie flat because this top panel, this top face has to lie somewhere. And then what does that leave? That leaves this hole, this tiny square-sized hole in the middle of it. But there's 5 square-sized panels that need to somehow fit in there. And if things are to remain connected, they can't all fit in there without overlap. So this is one that isn't going to work. But what if we just think about one polyhedron at a time? How big of a job could that be? Let's look at these standard polyhedra. These are the regular polyhedra, the platonic solids, and think about unfoldings for these. So you can look at, in the picture, you can see that every one of these has an unfolding, has a valid unfolding. And in fact, even stronger for these ones, every single unfolding, every single edge unfolding of these occurs without overlap. So these are really the best possible case. Let's talk about what I mean by every single unfolding. So let's think about the tetrahedron first. So the tetrahedron, you can see this one unfolding, and maybe you could imagine the center triangle as the base of the tetrahedron, and then the 3 sides folding flat in order to create this larger triangle. That's one of the unfoldings. But you can create the same basic shape if you chose, let's say, this front face to be the center of the tetrahedron, the center of the triangle, and then folded everything else around that. So actually, this picture represents 4 unfoldings of the same nature, but we're going to consider them all to be the same type of unfolding. So when we're thinking about the tetrahedron, there's actually 2 fundamentally different types of unfoldings to have. There's the one that results in this larger triangle and one that results in this parallelogram. So we have 2 of those. Does anyone have questions so far? Not yet? Okay, so we also know the answer for the cube. There's 11 different categories, different types of unfolding. And since the octahedron is dual to the cube, it turns out there's also 11 unfoldings in that case. So given all this information, I'd like to just ask you, can you make a guess? How many unfoldings do you think there would be for the dodecahedron, which has 12 sides, or the icosahedron, which has 20 sides? Do you want to try to guess, like, look at this trend? Maybe a second. If you don't feel comfortable typing in, you can just sort of think of a number in your head. 2,000, okay, close. So 43,000 different possible shapes of unfoldings. Remember, each one of these itself represents a bunch of different ways to get that particular shape. So, so the combinatorics, it just blows up. It's a really complicated problem to try to do brute force. And oh my God. And but people have tried, and there's many brute force examples where people have just taken the some polyhedron, tried all the different possible unfoldings by computer, found one that doesn't overlap. So there's a family of things that we know work. We still don't know the answer. And you might wonder, well, what do mathematicians think? Do they think it's true? And well, there's convincing evidence for and against it. So I'll just briefly say, so in 2007, for example, Demain and O'Rourke did a lot of sort of computer experimental evidence. And from these computer experiments, it seems that if you take a random polyhedron and a random edge cutting of that random polyhedron, the probability that that particular one unfolds without overlap, that unfolds with overlap goes to 1 as the number of vertices goes to infinity. So the more complex it is, the more likely it is that any random one is going to have an overlap. So that implies that it's less and less likely that you're going to accidentally, that a random choice will work. So, so maybe we'll get pinched out of it as the number of vertices go to infinity. On the other hand, in 2012, Gomi proved that it's not the combinatorics that would be in trouble. It would be an issue of geometry, and here's why. So every convex polyhedron, every unfolding of that, whether that unfolding has overlap or not, there may be a different unfolding that doesn't overlap, but let's just consider one that does overlap. There's some affine transformation, there's some stretch that you can do that will relieve that unfolding. So it's not the combinatorial structure of the thing, it has to do with the actual geometry if there's an issue at all. Okay, the point is we don't know either way, and that's what's fun. That's what's fun for mathematicians, is it's still a mystery. And it just keeps you coming back for, trying to figure it out. Okay, let's talk for a second about the shape of our universe. So when I say the shape, I mean two things. I'm talking about curvature, but I'm also talking about topology, the way a shape folds in back upon itself. And I can't remember now if I mentioned this, but part of our sculpture refers to an unsolved problem about the shape of our universe. So that's why I'm discussing this right now. So when I talk about curvature, I'm really talking about geometry. And there's 8 different possible geometries for 3-dimensional spaces, but 5 of them have a preferred direction where the measurement is sort of different one way than the other ways. And we don't really believe that the universe behaves that way. So we settle upon the 3 that are called isotropic, which are the same in every direction. Here's a 2-dimensional analog, image of 2-dimensional analog, spherical geometry with positive curvature, hyperbolic geometry with negative curvature, and then the sort of the very boundary case with exactly 0 curvature, flat Euclidean geometry. The 3D analog of those are the ones that could happen for our universe. And the cool thing about this is if the space is spherical, then it's definitely finite without question. But at spherical geometry, our universe is finite. And that's exciting to me. If it has hyperbolic or Euclidean geometry, well, it could be finite and it could be infinite. We don't know, it could be either. Okay, so you might be thinking to yourself, wait, how could our universe be finite? When I go outside and I look, there's no limit to how far I can see. It sure looks infinite. My eyes are telling me differently. And so I want to try to give you a feel for how the universe might be finite and yet still appear infinite to us. So imagine that this small finite universe, very tiny finite two-dimensional universe that consists of one little spaceship, looks like about 4 stars, 5 planets, and that's all there is to this little finite universe. But imagine that it's connected together in this interesting way where the front face is connected to the back face. Have you ever played like a video game, like maybe Asteroids was like this, where if you fly off in this direction, then you end up sort of coming back in from the other side? Imagine that the world is glued together that way, so that if this spaceship were to fly off forward, they would come back in from behind. So what's the spaceship going to see if they look forward? Well, their line of sight is going to follow the same thing, and it's going to wrap around, and they're going to see the back of their own spaceship. If they look upward, they're going to see the bottom of their spaceship. If they look downward, they're going to see the top of their spaceship. If they look back, they'll see the front of the spaceship. In fact, in any direction that they look, they're going to see a copy of their spaceship. If you're a rider, exactly like walking around the earth in a straight line, but you sort of end up back in the same place. So you could go forward and it would seem like you're going in a straight line, but in which you are, it's a geodesic, but it leads you back to the same location. Yeah. Okay, so anyways, it appears to this person whoever's riding around in the spaceship that there's infinitely many spaceships, infinitely many stars, and they don't know that they actually live in this very small finite world. Okay. Well, is this true? Well, I'm just going to say briefly, well, we don't know. And there was some data in 2002, where a probe was taking data off of the cosmic microwave background radiation. And if I had more time, I would go into this more because I just love it. But this data seemed to imply that space had positive curvature. And as I said before, that's super cool, because if it had positive spherical curvature, then it's finite. And we know what they all are. So we could just try to compare and see, well, which one is it most likely to be? And it turns out, due to some missing data, missing values in the data, the Poincare dodecahedral space is the one that best explained this, the data coming back. And so that's what we modeled the inside of our sculpture like. So let me just say, what would the Poincare dodecahedral universe look like? Here's a beautiful, beautiful image produced by this program called Curved Spaces by Jeff Weeks, of life inside the Poincare dodecahedral universe. Just like in the previous picture, all of these images of the Earth, this is the same Earth. There's not infinitely many Earths. There's just one Earth, and you're just seeing images of the Earth based on the way the space is connected. So the connection, just briefly, is, the top of the dodecahedron would be connected to the bottom with the 2/5 twist. So if you came out the top, you would come out the bottom a little bit twisted, and the same for every opposite pair of faces. Okay, later in 2014, more data came out, and that said what the curvature was in 0.4% of flat, which means it could be on either side. So it could be spherical, middle, or flat or hyperbolic. So we don't know. Poincare dodecahedral space still possible. So is everything else. I saw a recent paper saying there's more evidence for a finite universe. Anyways, this is still a big open question that I think is fascinating. I want to live in a dodecahedron. Maybe we do still. Maybe we do. So our sculpture tried to simulate this with mirrors. Obviously, we weren't able to build something that connected that way, but the mirror reflections was meant to give a feeling of that sort of thing. All right, the iRobot theme, I'll just say briefly. The students' vision, which I think was lovely, is that more and more we've been communicating with one another through technology, and that's never been more obvious than today, when here I am in California communicating with many of you at Wellesley about this, or wherever you are at home about these ideas, thanks to this technology. So it's been a conduit for communications, connected us. But at the same time, it may have walled us off somehow. So we stay inside our homes. We only communicate through this. We don't communicate as much face to face, and it's sort of fragmenting people from one another. So they envisioned each wall of the dodecahedron to represent some kind of technology, and then the folding up of the walls to be at one separation of us from the rest of humanity, only to be able to communicate through this wall of technology. So they called the project Unfolding Humanity from Technology, and we shortened it to Unfolding Humanity. Okay, so this is why we added the matrix ring on the outside, because to me, this seems to be the most iconic image of man being tethered to the machine. And we thought this would be something that would communicate that to everyone who saw it. And then on the inside, the mirrors provide a reflection of ourselves. And what's more human than just seeing infinite reflections of our own self? Okay. Now I'm excited to tell you about the creation of this project. So I had this idea of what I wanted to do, and then I knew I needed some money, so I needed a budget. And then with the budget, I needed to know what it was going to be built out of. I needed a design, and then then I needed to know what materials made the most sense, and realizing this requirement of it surviving 100-mile-an-hour winds. I needed an engineer, and lucky for me, I found a wonderful engineer in Gordon Hoople. He took over. I submitted sort of a very weak, I think, idea for the first proposal of what I thought it could be made out of, and he came in and he said, "Okay, no, here's what we really need to do." And he made a beautiful model in SolidWorks, and a bunch of students helped with this model, and it was really solid. So. So he suggested that we start making a prototype face. So this is one that we built from by hand. And in this picture, there's a couple of, here's some students, Sydney, Christina, and Nick. And here's a faculty member who joined later on, a member of the community. And we learned a couple of things. One thing that we learned is that it's very hard to cut an accurate pentagon by hand. The angles are kind of weird, and it's so huge, and it was kind of wonky. But we also learned that at this scale, so this is a 7-foot tall pentagon, it's pretty flimsy with a wooden interior, and it wasn't going to stand up to the winds. It wasn't going to stand up to people climbing on it, which people do as part of participation at Burning Man. So we needed internal steel framing, and students learned how to weld. And they went to it, and they welded the frames. This took them a lot longer than this video is implying for each one of these. But they did a great job. So we had solid internal framing. Yeah, so cool. They learned how to weld. Really, they did such a good job. The students did some of it. There was also this wonderful volunteer that I can't fail to mention, named Sean Pennington, who came in and every day after work and did a lot of the welding for us too. It was really a wonderful collaboration. We also needed for the one skeleton, one of the challenges was the vertices. So the vertices, these trivalent vertices, this angle between the edges is 108 degrees. And this isn't something you can just go to the store and buy, something with a 108-degree angle to it. So we had to construct it. And the fear of constructing it is that if you're a tiny little bit off, if you're 107 degrees, well, what's going to happen? You've got your vertex here, then you've got a 4.5-foot long edge, and then there's another vertex. And then as you build this giant thing, this air is going to propagate. And when you get to the other side, it's not going to come together. So, so we really needed to have precision here and also some strength. And this is the way things work out sometimes. I really felt lost here until I met a person who not only had built a dodecahedron before, but was a welder. And so we got him to do the welding of the vertices for us. Here he is. This is Wizard. He flew down from the Bay Area to help assemble it, just to make sure that there wasn't any problems with the vertices. And you know what? They were perfect. It just came together perfectly the first time. And And it was so strong. I mean, so we wanted to test it, because it's going to hold. These are steel. It was 2 tons. This project. We wanted to be sure it was sturdy, and so this is 10,000 pounds of pressure. I don't know if you can see this tiny little meter, but almost 10,000 pounds of pressure, that a force that this thing is withstanding. And you can see the steel poles are buckling a little bit, but the welds are fine. So we did a great job. Students did so many other things, in addition to the computer engineering and welding. They put anti-rust things on, they painted, they glued mirrors. I mean, there was a lot of work to be done. At the same time, I was at CoLab. So we managed to get a grant from San Diego Collaborative Arts Project. And as part of this grant, we got some build space at this maker place, a community maker place that had a lot of really great equipment. So I love CoLab. Yeah, it's so good. We wanted the external faces to look like a computer screen. So we had to have a bunch of holes in each face. And we needed a more perfectly shaped pentagon. And so we used their machine. This is a CNC router, which you can see to cut these little windows in. And our students learned to operate it, and they cut everything out for us. And that was wonderful. Here's some people, we had to paint it black so that it looks like the background of a computer screen. Painting the front wasn't so hard, but you can see inside these little windows, oh my gosh, painting around all the insides of the windows, that was incredibly labor intensive. And here's these wonderful volunteers. Here's Paul from the community. Here's Victoria, a student, and here's Serena, another student, doing this painting. And one thing you can see in the background, this is the prototype face that we created. As we were sort of trying to learn what we were doing. And you see these acrylic characters in the prototype face. Well, so there was 224 per face, so 2,240 total. We didn't put characters on the ceiling or the floor. And they all had to be laser etched. So we learned, I and a bunch of students and community members learned how to operate the flatbed laser. And we did 72 characters at a time. And that took about an hour and 20 minutes per batch. 2,240 characters. Again, this was a lot of work. We glued the characters in to strips, in strips along in the holes. And then we had to illuminate them somehow. So I'm wearing something. I don't know if you can see this glowing. This is just like one of the characters, and it's etched by the laser. And I don't know if you can hear that, but that's the etching behind it. And so how is this illuminated? It's very bright in the dark, but now that it's light here, maybe you can't tell. There's an LED that's shining straight out the edge here. And so when it shines through the part that doesn't have any etching, there's no disturbance. It just goes right through. But when it hits the etching, the disturbance is what makes it glow. And so that's what we made. That's how we made the characters light up. So we had to put LED strips along the side of each of these character columns. And with the pentagon, they're all different heights. So that meant a lot of custom soldering. So here's some of our wonderful volunteers. Here's Stephen and Ross, who did almost all of the soldering for us. And here's Cindy, Stephen's wife, who was helping with sort of organizing that part as they were going. Sajana is helping with testing each time that somebody put another connector on to make sure that it worked before we wound it up. Here's Laurel cutting new strips. Okay, so I was feeling pretty good about this progress, and the animations on this were much less complex than for the Journey project, and I thought, okay, I can handle those. But then at this point, I realized there was a fundamental piece I was missing, which was electronics. I didn't know anything about. I didn't know anything about how much power I would need, how to set that up, how to connect it to a generator, how to wire things, nothing. And so I sent out a request, off into the void, can anybody help with any of these things? And luckily, Max showed up, who just knew absolutely everything that I needed him to know. I mean, he was able to help with all those things and more. And he was a huge part of this whole project. especially, I mean, from the electronics point of view, but he also wrote the code to have all the controllers communicate with one another, and just left me to do the fun part, which was writing the animations. And so I'm really grateful to have had him join. Here's other people adding more, adding the wiring on to each of the panels. There's 20 of these panels. And this is, oh, wait, let me go back for a second. Before I run this animation. So right here, I don't know if you can see, it's maybe a little bit smaller than a pack of gum, or about the size of a pack of gum. This is the controller. This is a little computer that runs the animation. This little piece here is, it's easy. And this thing right here is a radio, so that each one can communicate with each other one, so they can stay synced if they need to. And this is sort of the inside of it. And you can see each of these has 5 LEDs shining into the side of the character. And this is what it looks like when the animation is running from the inside. So just in summary, a bunch of data, 2-ton metal, wood, and acrylic, about 12 feet tall, 16,000 programmed LEDs, 25 microcontrollers, about 65,000 person hours invested, 6,500 person hours invested, 45,000 grants and donations. This was a big project. This was much more than I really envisioned when I started. Here's what the build looked like at Burning Man. So they moved us to this sort of dried patch of lake bed, and they used GPS to say, here's your spot. And so I nailed down a marker to show, where we were allowed to build. And we started. So the first thing we needed was to get what's called heat out, heavy equipment and transportation. And they came out to dig these giant holes in the playa. The playa is like almost like cement, like it's very hard to dig into. And so there are these 4-foot tall earth anchors that they grind into it so that you can clamp yourself down to it. So when these winds come along, you don't have to worry about your dodecahedron just rolling away. So, so they came to do that. This thing over here is a trench off to the generator, which they also dug for us. And then we started the build. So this was all human powered from here. The scaffolding, all the assembly, the steel was quite heavy and needed people to help lift it. And you can see it was a dusty day. The wind was blowing pretty hard actually that whole week. And yeah, we started the build. And after the frame, we had to put the faces on, and these faces are about 250 pounds. So we needed a lot of people to lift it. We wanted to be careful to not scrape the inside because the inside was mirrored and we could scrape it on the scaffolding. So here's a bunch of volunteers being careful to to get it up there safely. We put the panels on the outside, and then it was time for Max to go to work. So so Max had to set up all the wiring on the inside. So I don't know if you can see here, this right here is the power cable coming from the inside of that trench you saw earlier into the inside of the project. And Max is just starting to set up connections to all the controllers that will run the thing. I had the honor of connecting the final LEDs on the top, and then we were done. Chance to celebrate. So we had some champagne. We had, oh, now you can see how well the pendant glows at night. This was our first chance to ever see it fully assembled because we didn't have time before we left. And it was also our first chance to see what the mirrors looked like. So I'm pulling the plastic off the mirrors so we can see. And now it's time to celebrate. So this was our first view of it. So here is, I think, everybody who was on the playa build. Maybe there's some people missing, but I think this is everybody. And you can just see how excited we are. I mean, it was so cool and cooler than we even expected, and exciting to sort of be done. And yeah, so that was really wonderful. And so how did it come out? Well, this is what it looked like. And I still find it so beautiful. I didn't, you have this idea in your mind of what it might be, but you just don't know until it's built. And I spent a lot of time there just sort of staring at it. Yeah, it was really wonderful. And so, I'll show you a couple of pictures. This is a different picture that somebody took and sent me. There'll be, I think, a little video of somebody who's opening up oh, maybe you can hear that, who's trying to close up one of the faces. So it turned out, even though the sculpture does open all the way, we didn't want to do that on play because it was so windy. We were afraid it was going to, rip one of the things off or hurt somebody. And so we clamped everything down except this one face that people could open and close to get inside of. But I do have a picture elsewhere at Maker Faire. Here's a picture of it opening up, just so that you know that we're true to the mathematics. It really does. And if you're worried about these two faces that don't open up, well, they're required to keep the whole thing connected. So that has to be part of it. Right. This is the view from the inside with all the, it was lovely at Maker Faire. Yeah, this picture is actually at Maker Faire after we cleaned it up a little bit from all the dust from the playa. And these are what all the reflections looked like. I tried to make some animations that space seemed to me like a comet or twinkly stars or something like that. Here's a little bit about what the reflections look like with people in it. I didn't realize at the time that if you're ever going to show these to people, you should do it landscape-wise rather than portrait, but this is what I have. And people were there at all times of the day and all times of the evening. So here's people, early, like mid-evening. This is 1 a.m. I came by at 5 a.m. and there's people here. Sunrise, midday, even late afternoon. There's not very many people late afternoon, but it's hot there. And usually during the day, people tend to stay more in their camps and trying to shelter from the heat, and then they go out more at night. Oh, and you can see, maybe this helps give you a feel. You may have felt like this was a really big structure, but when you see it on playa, it looks kind of puny. And it was one of the smaller ones. I mean, there's many other, this nearby one that's not in the picture was a spire of cars stacked on top of one another that towered over ours. Here was an unexpected benefit of doing this, actually. This project inspired joy. And I wasn't even thinking of that. I wanted it to inspire curiosity and conversation. But seeing the happiness on people's faces, look at their expressions. It was just, it still gives me goosebumps to think of that I contributed to something that just generated happiness. That was really wonderful. Feature of it. Joy and also play. So these people are closing themselves in and sort of counting down like they're in a spaceship and ready to blast off. Other people treated it as a time machine and were choosing like where and when they wanted to end up. Some people just came and sat inside, closed themselves up. I think told stories. I think these people told did magic tricks, laughed. Lots of times I'd go by to be closed in, and people would be like, how did you get in there? And they couldn't see how it was closed. And so it was fun. Actually, one little story I want to tell you is that a person came by and said that he'd been in there. It was one of the last nights. He said that he'd been in there for 6 hours the night before, and that he sat in there and there were all the mirrors and this reflecting his own image back to him made him very introspective. Made him sort of self-reflective. And so he would call people in as they go by, and then one by one, a person would come in and they'd have these conversations, these sort of deep conversations, and that person would leave and he'd call someone else in, and he was back the next night for more. So yeah, that was really exciting. I love this video. This video, I think, shows the curiosity. So I won't have the sound on, but I know what they're saying. This person is asking, what's the meaning of this project? The next woman is asking, how many reflections can you see? And many other questions were asked. And so the curiosity was there. And one thing that was, I think, even better is that follow-up questions were asked. Normally in my day-to-day life, if I say something about math, if they ask a question and I say math, that's the end of that conversation. But here I would say, well, it's an unsolved math problem. And they'd say, oh, really cool, which one? And then I'd tell them, and they'd say, gosh, I wonder wait, why don't they just know that? Why don't they just test it? And, you had a really chance to really interact with people who wanted to know. And To me, that's what made this a real success, is that it really did communicate to a group of people who had curiosity and drive what it was that mathematicians are interested in and sort of are compelled by. So that felt like a success. So let me just, in summary, let me just tell you, if there's anything I'd like you to take away from this talk, this is 3 things. So one, if you ever think that you might want to do something like this, connect to your local art community. Our art community in San Diego is wonderful. They're so talented, they're so creative, they're so open and giving, and we got so much just learning from them and volunteer help from them, and just good feelings all around. It's a very, very productive and positive experience. And you'd be surprised how many artists are interested in mathematical topics. So it's a really good mesh of people, and I really recommend that. Also, I think it helps to introduce the physical aspects of mathematics to students. I think there's something to learn. So for example, this person Wizard that I met, who did the vertices, he said, well, it's weird that you chose the dodecahedron, because that sags. And it does. And in our models, it kept sagging. I was like, yeah, I didn't expect that, but of course that makes sense. The icosahedron is made of triangles and those are rigid, but the dodecahedron is pentagons, and those pentagons can sag under weight. And so that's something that I should have predicted, but I didn't really see until we actually had the physical model. So this is the sort of thing that we can gain from that. And I guess finally, be bold. This was a huge project and I was in no way qualified to do it. And I just learned as I went, and people showed up just when I needed them. And I think I think you should find comfort in that tends to happen. And so I'd like to encourage that. It couldn't have been made possible at all without the volunteers. So there was more than 80 volunteers. Lovely cross-section of the community. I love this picture in particular because it has, here's Erica. She's a student at San Diego State in art and I think computer programming. Here's Ross and Steven from San Diego Maker Guild. Sean is in IT. There's Max, who was at Sony. Eduardo is a student in engineering. He's just graduated from USD, who helped a lot. Here's Karen Tang. She just showed up from LA randomly and said, hey, can I help? And so she came to help that day. Ben's a graduate student in math at UCSD. Paul's a community member. Sojana's a wonderful community member who's become a friend of mine, a good friend of mine, who's just wanted to join to see what Burning Man was about, to see what the people in San Diego were about. Susie is a theology and religious studies professor at USD. So it was a real collection, a cross-section of people who came together every Monday night and Saturday daytime. And it wouldn't have been possible without them. And so I just want to acknowledge their contributions and thank them all. And also thank you so much for listening to my story. Stanley silent clapping.
Thank you
so much. Does anyone have any questions?
I have 1,000 questions, but
okay.
Does anybody else have any questions? There are just so many things to ask. This is incredible. I hope you all enjoyed the talk. Please feel free to ask questions either in the chat or unmute yourself, please.
Overwhelming.
I'd really like to ask a question about the collaboration, if that's okay, Diane.
Oh yeah, absolutely.
The project is wonderful, but what really blows me away is that you didn't have to do it yourself. Even if you could have done it yourself, you didn't have to. Somehow you got, and this is what you did that was magical, that I think you undervalue. I don't think many people have this ability or have pulled this off, or at least God knows I haven't. I mean, once in a great while I have. But what you pulled off here was getting all of these people to spin in the same direction and to come together and do this. And I'm just curious if you have any thoughts about how did you do that, or what was it that made this happen? What were the forces, the social forces, that got everybody to pull behind this one cart?
That's a wonderful question, and I have a lot of different answers which are all guesses. which I sort of can't necessarily support with facts. But one thing I have to give a lot of, I appreciate all the credit you're giving me, but I really have to give a lot of credit to, I think the culture in San Diego related to CoLab, and also the culture of Burning Man. I mean, the culture of Burning Man is, you give, you step up to help, you see what are some things you can be involved in, participation. So CoLab, where most of this, where half of the building took place, is sort of a hub for people related to Burning Man. So people look, or, how can I contribute? I would love to be part of something. And so there's sort of a ready-made audience of people who want to be involved in things. So it was really, and I think I also, having been with the Journey Project and seeing how many people showed up with maybe I didn't know, maybe the people on this project, I guess there wasn't that much overlap with the previous project, or even any overlap, but maybe I had some credibility having been on the previous project. And so I don't know if that gave people more of a reason to trust that this would become something, or maybe they just thought it looked cool, or I don't know. I just put posts on some burner Facebook pages and also on the CoLab pages. And I just said, here, every Monday night and Saturday daytime, we're going to do this. And people showed up. And I wasn't sure about, I really needed somebody to do a lot of soldering. That was very labor intensive. And there's a person here, James Newton, who's on this, who's watching this talk right now. I contacted him directly. He's up in North County, and he said, oh, let me put it out to the North County Maker Guild and see if anybody wants to help you. And people drove down, it's kind of a long drive, and drove down to help. So,
we were happy to help out with that. Can I ask really quick, were the students, were they incentivized in terms of like their credit or internships or anything like that?
Yeah, that's a good question. Four of them were. So Michael Sween, Sydney, Ava, three of them were. And Alex helped, volunteered over the summer, but I think he didn't have funding. Yeah, so three of them were funded as like a summer research experience.
I think two of the students came out to one of the maker fairs that we put on and had a table and kind of.
Yeah, that's right. But those were different students.
Oh yeah, I was asking them if they got credit or anything for it. They were like, no, we just thought it would be fun to come out and do this. So it's a good.
So
it actually inspired another. So these two students that James is talking about, they did models, like there were little lamps, dodecahedron models with the infinity mirror in it, and they figured out how to use the table saw and they figured out a way to cut things at the right angle, and they made these really, really beautiful objects on their own as gifts to people who gave $1,000 or more to the project. And so they worked, and Eduardo volunteered and even showed up on Playa and volunteered time. Eduardo's here on this call. A lot of students, Victoria didn't get any credit, Serena didn't get any credit. I could probably name 10 more students who just were interested. They wanted to learn something, they wanted to be part of something, and they came to help.
I want to make sure that we have time to give our students a chance to ask some questions. Students, do you have any questions? Comments, impressions? Well, our students are very shy, I guess.
So I think Sarah raised her hand. Let me, okay. Could you, I can't find the participant list. Sarah, yeah, I'd like to hear what you have to say.
Hi, yeah, I had the same question that was in the chat, which is like, what happened after Burning Man? Like, I guess, like, how did you deconstruct it? Did you ever like reconstruct it? I guess you did for the other pictures. I'm just interested in what happened after.
Well, yeah, so that's a great question, and I'm interested in that too. So I see, so we had to disassemble it and, leave no trace. We had to be careful to pick everything up and take it with us. And then it was very, very dirty, as you can imagine. So we cleaned it and we reassembled it at San Diego Maker Faire in town. and it was there for 2 weeks. And then we pulled it. And I've been trying to find a permanent place for it. And there's a lot of people who are interested. But when they find out that it's 12 feet tall and it really can't be outside, can't be in the rain, the electronics aren't protected, that really limits where it can go. And so there's been some really cool art, experiential art things who wanted to have it, and they wanted to see, could they pay us to protect the electronics, or could they, and they were going to take it inside this place in Manhattan, but it turns out that the floor of the old building couldn't support 2 tons. So so we're having a hard time placing it. Right now it's in Vegas, disassembled in a warehouse. I was hoping to get it into this new experiential art and retail area called Area 15. And that may still happen, I'm not sure. But I tell you what, if you have a good idea, I would love to hear it, because I want it to come to life again. I really want it to go somewhere. I'll donate it to wherever it is. I don't want money for it. I just want it to be experienced.
You can think about bringing it to Wellesley. Who knows? Any other questions?
Sure, if you find a place for it, I'll get it there.
The new science center, they're still building it.
Yeah, we have a new science center. It's still being built, and there's space. So I have a few questions. I don't want you to have to spend a lot of time answering them, but a quick answer. First of all, how did you decide how big to make it?
Okay, that was a great question.
Yeah.
Yeah. Well, I wanted it to be. I was thinking that 10 to 15 feet is a height. It's sort of a standard height for a smallish thing out there. So that seems sort of the right range. And Gordon, the engineering lead, he kept saying, let's make it smaller, let's make it smaller, let's make it smaller. And because it made the engineering easier, made it lighter, made everything easier. And I was like, no, let's go bigger so people will see it. And I think there was sort of a trade-off also in terms of money, like steel costs. And so the bigger you make it, the more expensive it is. I was just thinking, I wanted it big enough that a group of people could go inside and close themselves up, and big enough that it could be seen from far away, that you'd be biking by and be like, whoa, what's this? And you'd sort of steer yourself towards it. And then not so big that physics would prohibit us from constructing it. So.
Okay, my second question is there a higher dimensional analog of the flattening conjecture? In other words, is there a version that says a 4-dimensional polyhedron can be flattened into a 3-dimensional space?
Yes, and I don't remember all the details, but this is something that my colleague Sethian Devadas, who helped me come up with the idea in the first place. He had a group of students over the summer, that same summer, investigating that question. So he's got some answers about that. Unfortunately, I don't know what the answers are, but there is investigation about that and some results, whatever those results are. And it's Sethian Devadas who's the guy to look to. And I can find the paper and send it to you if you want to.
And I guess an obvious question is, what are you going to do next?
Oh, well, in the meantime, Max and I did the lighting. So Max is actually here on the call. I don't know if you can see it. This person sitting in front of this thing that looks like a bunch of fingers coming out of the ground that are lit up. Yeah, we did the lighting on this bridge, and we actually just got some surviving COVID. That is a big goal for now. Yes, absolutely. But our collective actually just got a grant from San Diego to build a community-based art sculpture in one of San Diego's parks to try to bring people back to parks after COVID. So we just got that grant like a couple of weeks ago, and so we'll be building that this year. And but I really, and I'm going to love it, but I really, really want to get back to mathematics. I'm waiting for the next. I have an idea of what I want to do next, of sort of a mathematical sculpture that will sort of pose an unsolved problem that will be intriguing. So please, if anybody who wants to be involved, I'll find a way you can help long distance. Seriously, just contact me. And it won't be this year, but probably the year after. I'd like to do that. And I'm being cagey about my idea because I want to make sure it works before I let it out into the world.
Right. Anyone else have any questions or comments? So It's been a delight having you here, Diane. In a way, I'm not surprised you managed to pull this off because you've always been the type of person who could run with something, not just run with something, but get the community to back you up and explain it in a way that makes everybody excited. But thank you so much. We all wish you luck in future projects, and I hope that you'll have some kind of home, virtual or physical, in the Wellesley math department, right?
Oh yeah,
Yeah.
I would love that, seriously.
Yeah, definitely.
Okay.
So
Well, thanks so much, everyone.
thank you all the students for your attention and guests.